Hello, today we are going to talk about how to measure frequency agile signals on the Rohde & Schwarz FPL1000 spectrum analyzer. The FPL1000 can have 40 MHz analysis bandwidth, and thus it can analyze any signals which are hopping, chirping, or otherwise varying in frequency over that bandwidth. So let's get started with our demonstration. The test signal that I'm using for our demonstration is a frequency modulated signal with a linear ramp. In addition, it is a pulsed signal such that during the on time of the pulse, the chirp modulation is active. And this signal is often called a linear FM chirp, and it's common to need to analyze this. So looking at the analyzer, we are in a preset condition with a signal described already coming into the front. And so I can just tune the center frequency to the frequency of the chirp. I can set my span to be 50 megahertz. And we can see there's something going on here already. I can quickly go to the trace menu and set it into max hold mode. And with max hold, it'll start to fill in the spectrum. And with a simple occupied bandwidth measurement, we can see down below here that it's roughly 40 megahertz as we expected. So that's a great way to quickly see what the spectrum looks like. Then the other part you might want to look at is the time domain behavior. So if we go to another tab on the analyzer here, we have the IQ analyzer mode. And so what we can do again is set our bandwidth to 40 megahertz. We can set our measurement time to say 500 microseconds. And we're starting to see some time domain behavior. A couple other things we can try is to stabilize the signal with an IF power trigger since we have a pulse signal. So now we can see 3 different pulses. Maybe we don't know what's going on during the pulse, but we can at least see the power versus time with this mode. So to get a little bit better idea of the timing, I can use a couple markers. So maybe I'll look for another peak with the marker. We'll go to next peak one more time to get the center one. So we can see the marker I just placed is at the beginning of this pulse here, right in the middle of the screen. And then I can set a second marker. And for example, if I set the second marker to 200 microseconds as it was there, we can see that this is the period roughly of one of the pulses since we're going from the start of this one to the start of the next one. And then if we go and change this delta marker to 100 microseconds, now we can see the delta marker ended up right at the end of this pulse here in the middle. So now we have an idea that our period is about 200 microseconds, the width is about 100 microseconds. So we know the spectral behavior and the time behavior, but we want to see how the frequency is changing during this time here where the pulse is active. So for that, I can get one more tab and go to the analog demodulation measurement mode. So in here I can put in a lot of similar settings that I had on the IQ analyzer. For example, 40 megahertz demodulation bandwidth, measurement time of 500 microseconds. And if I set my trigger to be power again, I get stabilized. And we are now seeing frequency versus time, but we probably need to change the scale to get a better look of what's going on here. So if I go to the scale configuration, and since we're expecting 40 megahertz of change, if I set 5 megahertz per division, you can see that we're going from down here minus 20 megahertz up to plus 20 megahertz in our frequency versus time plot. And one of the common measurements people need to make on these type of signals is the linearity of this frequency, linear frequency behavior. So again, we can use the markers. First thing we can do actually, since there might be some noise from the full 40 megahertz bandwidth capture, we can go into the bandwidth and maybe put some filtering on the video signal. So this is the signal after we've demodulated the frequency. And so you can see that in this period here, we have a lot of noise just because there's no power in the signal. But in here, we're seeing the frequency variation. It's been smoothed out a little bit due to the video bandwidth. And so to get a basic idea of the linearity, again, we can use our markers, and I can drag this marker over somewhere towards the beginning of the chirp, maybe after it's settled. And then I can put the second marker at, say, 75 microseconds. So I've got two markers 75 microseconds apart. We learned previously that this is a 100 microsecond chirp signal. So we did 3/4 of the time. And if I take a look at the delta frequency between the two, it's 30 megahertz, which happens to be 75% of the expected bandwidth. So we know in here we have a nice linear chirp as expected. And the final thing you can do is if I just click on this multi-view, I can get all these different modes, the spectrum, the time domain, and the frequency demodulation all in one shot. And I can even turn on the sequencer, and we can sequence between the different measurements and get a great overall picture of the signal. So in conclusion, the FPL1000 from Rohde and Schwarz provides great capability for analyzing frequency varying signals on an instrument with RF performance that is best in its class, with a modern user interface and an attractive price point. Thanks very much for your attention.